Okay, so we're going to talk about chemical thermodynamics, and in a general chemistry course, you often talk about thermochemistry. So that is all to set you up to be able to understand how things change in response to different energetics. So thermochemistry is really just tabulating what the different bond energies for reactants and products are, and whether or not you would expect energy to be released in the form of heat or energy to be added to the system for it to run. That's really the extent of your Chem 107 basic knowledge. And we did some examples of using Hess's law, which were like, how do you add up all the different reactions to see what the overall energy change of the reaction is, etc. But now we're drilling into, even if we know the thermochemistry of the system, how do we understand if a system is actually going to react? So far, our general understanding of chemistry can be broken up into three primary categories. And honestly, this is true for all chemistry. If you have a good sense of these three ideas, you can understand any type of chemistry. So the idea of kinetics tells us how fast a reaction is going to proceed. Equilibrium tells us how far it's going to proceed. When is it going to stop? So the extent, and in some cases the direction. Whereas thermodynamics tells us what is the energetic driving force? What is the thing behind it that's actually pushing it to reach an equilibrium at a particular rate? And so these are the three big ideas. Thermo is energy, equilibrium is extent, and kinetics is rate. And in reality, thermo is connected and the cause of both of these. So now that we sort of understand conceptually and intuitively what in kinetics or equilibrium are, we need to go back one step and think about, well, what actually dictates something like K? Or little k for that matter, the rate constant. How are those things related to the actual energy change in a system for a reaction? So the first thing we need to talk about with chemical thermodynamics is this idea of spontaneity. Spontaneity means whether or not a reaction will proceed, as written, from reactants to products without any energy input required from the universe. So spontaneous reaction means no energy input required. And so I'm going to draw up two different potential energy diagrams or reaction progress diagrams, just like we thought about before, where we have reactants and our products noted by these horizontal lines. And sort of generically, to start with, in the spontaneous case, we can think, okay, well, for the reactant, if that's at a higher energy, potential energy than the products, which really means that it has more bond energy in the system, then the delta E is going to be negative, meaning this is something the universe likes, right? We always want to move towards a lower energy system. It doesn't matter if it's chemistry or physics or biology or whatever, that's always the goal of the universe, because that is the driving force of the universe, high energy to the lower energy state. And in our discussion of rates and chemical kinetics, we talked about, well, it's not really as simple as just the difference between the energy of the reactants and the products. It's actually, we've got this little bit more nuanced thing called the activation energy. And the activation energy is this barrier, which is to the top of whatever that transition state energy is, which comes from collision theory. And in this case, we call that activation energy. I just drew two examples here. Maybe the second one, the lower one, is with a catalyst. And the example here shows that, well, in this case specifically, this is still spontaneous, but it's maybe slower, right? Because it takes the reactant more attempts and more kinetic energy to get over that original barrier. This lower one is spontaneous, but maybe it's faster because it actually doesn't have probabilistically as many possible attempts to get over that barrier to produce the products. In either case, the spontaneity just means that the overall potential energy change for the system is decreasing, which just means that the universe doesn't need to provide any energy for this reaction to just happen spontaneously. What's important to know, though, is that this tells us nothing about the rate at which it will occur. If we have a difference in energy between reactants and products, we'll say, yep, that's going to be a spontaneous system, but we have to know specifically what that activation barrier looks like to have any commentary on the rate at which it would get there. An example of that would be, say, the reaction between iron oxide and aluminum. This is rust and aluminum. These things are probably in some form in the room that you're sitting in right now. Turns out these things have a huge energy difference to produce the oxidized version of aluminum oxide, and iron. And we call this the thermite reaction. And it is such an energetically favorable reaction that the reactants are way higher in energy than the products. So we would say, yep, that's a spontaneous reaction. The universe doesn't need to put any energy into it, but simply by saying that tells us nothing about whether or not it will occur at any appreciable rate. And the reality is that if I take some rust and put it next to aluminum, which you could probably do in the room you're in right now, you'll see that these things are not reacting at all, or at least to the naked eye, because the rate of this reaction is incredibly slow. It may take 1,000,000 years for it to occur, but it's still considered spontaneous. And so it's important to understand the nuance between something that has an energetic difference, which may be considered spontaneous, but something that can still be considered slow, and all that's going to be modulated by that activation barrier. And then in contrast, a non-spontaneous system, one that needs energy from the universe to occur, is something where the products are at a higher energy than what you started with. And this should make some intuitive sense in your mind, just as a human that interacts with the world, right? If you want an object at the top of Pikes Peak, you have to put it there by adding energy to that system. It's a direct analogy here, where this is Pikes Peak up here, and this is the object maybe at my house in Manitou Springs. I physically either have to drive up there, or walk up there, or fly up there. Any which combination is going to require energy input, literal energy input, either in the form of calories that I eat or fossil fuels that I burn, etc., to get the object up to here. Chemistry is no different. If we have reactants that we want to move to a higher energy state, we need to do that, and we consider that a non-spontaneous reaction.